let's try to sketch the curve of a rational function. Here I've got y equals 2x squared, all on x squared minus 1. The first thing I want to do is think about the domain of this function. So since I have a rational function, all I have to worry about is whether or not that denominator equals 0. My x cannot be positive 1 or negative 1, or else I'll be dividing by 0, which is undefined. So the domain of this function is all real numbers except for plus and minus 1. I'll also want to find the x-intercepts and the y-intercepts. And for this function, if y is equal to 0, then my x also has to be equal to 0 and vice versa. So this function will cross through the origin, actually. Now, for determining whether the function is even or odd, I just have to look at f of minus x. I'd have 2 times the square of negative x, but that's just 2x squared. I'd have the square of negative x minus 1. Well, that's the same as x squared minus 1. So this is an even function. That means that whatever I have to the left of the x, to the left of the y-axis, will just be mirrored across, and it will look exactly the same on the other side. Oh, cool. All of this information I'm getting just from looking at this formula and trying to understand what the algebra is asking me to do. Now let's get to some of the calculus material. Let's look at our horizontal asymptotes. As x goes to plus or minus infinity, I can look at the limit of 2 times x squared divided by x squared minus 1. But I can rewrite that as 2 on 1 minus 1 on x squared. So that's going to go to a value of 2. So we have a horizontal asymptote at y equals 2. And similarly, for vertical asymptotes, I know that I have trouble when x equals plus or minus 1. And I can check that these limits do go to positive and negative infinity, depending on what side of the function I'm on. So when I'm sketching, this information here will tell me exactly which way the function goes, whether it's up to positive infinity or down to negative infinity. So to sketch those in, my drawing at first, I give myself kind of this scaffold here where I have put in my horizontal asymptote and my vertical asymptotes. And notice that I can say that the function is above this horizontal asymptote here, and here, and it is below the horizontal asymptote here. And how do I know that information? Because I know that the limit as the function, as x approaches negative 1 from the left is going to be positive infinity, from the right, negative infinity. As x approaches 1 from the left, the function approaches negative infinity, and from the right, positive infinity. So I can say that this graph of the function should look something like fitting into these asymptotes. Okay, well, let's keep going. Where is this function increasing? I will compute a derivative. Here I will need to use the quotient rule. And after the dust settles, the first derivative of this function is just going to be negative 4x, all on the square of the quantity x squared minus 1. So if I want to have a positive derivative, then x has to be a negative number. And if I want a negative derivative, then x has to be a positive number, right? That denominator is always positive anyway. So the only thing that's determining the sign of this derivative, sign, plus or minus, is whether or not x is a positive number or a negative number. What are my critical points? X has to be 0 to make that derivative equal to 0. And since the sign of the derivative changes at x equals 0, that gives me a local maximum. So I'm starting to get an idea of what this graph should look like. I can also talk about concavity, where I'll have to take the second derivative of the function. Here, my second derivative is this other rational function. So we get that through another application of the quotient rule. Where is this positive and where is this negative? Well, that numerator is always going to be positive. The denominator will be positive or negative depending on, well, if x squared minus 1 is positive, the denominator will be positive. And if x squared minus 1 is negative, then the denominator will be negative. So it all comes down to whether or not x is greater than 0, greater than 1 in absolute value. So it will be concave upward as long as the absolute value of x is greater than 1, concave downward as long as the absolute value of x is less than 1. So I can fill in the rest of the picture like this. Here is my sketch of the graph. So I have these asymptotes, just like I was talking about. The function is concave up as long as x is either greater than 1 or less than negative 1. The function is concave down between negative 1 and positive 1. I have a maximum at 0, just like I got from the formula.